Hello, my name is Andrzej Surma. Thank you very much for the invitation. I represent GfK company. Our company has more of its representatives at the conference. James Pitcher will have his presentation right after me, and he shows the business application of the theoretical part I will present here. I'm a data analyst in global marketing science team. A few words about the company. GfK is a provider of data and advanced analysis to the customer goods industry. One of our product is dedicated to improve brand strength and monitor the brand KPIs. Most of us are probably aware of the importance of marketing in context brand perception on the market. The analytical task we are faced with is to understand what marketing aspect is the most important for client's brand. Marketing departments usually have limited budget. So in order to develop a brand, they have to focus on some characteristics of the product. But what feature of the product is most critical in driving its purchase? Its price, quality, or something else? Analysis to discover the importance of product features is often called driver analysis. It is supervised analysis. And these features are called predictors. The questions the marketing specialist wants to answer are: what is the hierarchy of the brand or product aspects as sales drivers? What makes the brand appear in customers' consciousness first? Even when we have the black box model that is able to predict our outcome very precisely, the next question that comes up is why? What is the reason of such prediction? Which aspect is responsible for such and not another result of prediction? Today, I will have a pleasure to present an overview of different methods, how calculate the importance of the aspects included in the model, and what is the impact of the data and common relationships between them on the importance results. The content of the presentation is divided into 5 parts. I would like to start from the presentation of the methods we can use to calculate the feature importance. I will only focus on several methods. Next step is dedicated to mathematical background of the calculation, how these methods deal with the calculation of importance. In third part, I will mention about the idea I used to compare the methods. Fourth part is actually method comparison, and at the end, I will share a few conclusions with you. The topics discussed in the presentation is extremely important for any driver analysis in market research. Clients are interested in the ranking of the operational marketing business aspects and wanted to know the difference between them. It can be also helpful as a feature selection technique to exclude these elements with low importance. This need most often occurs at the global level in a synthetic form. It means that client would like to get comprehensive and easy to interpret results. The purpose of this presentation is an overview of the available methods and compare the most popular ones. It's not simple to recommend only one, the best method, because it depends on the objective of the analysis. I would like to show which method is better in some particular situation and which should be avoided. In this presentation, I'm going to focus on the following methods. GfK's flagship driver analysis method for many years was Shapley Value Regression. Another method worth mentioning is total effects for Bayesian Network, taken from BayesiaLab tool, what I called here Bayesian Network. I also include here random forest importance based on impurity and known among Python developers shap algorithm. This last one is a kind of explainer, a method that helps to understand the behavior of the models. We can look at the available methods from different perspectives. Some approaches are directly related to target function. They are prediction-based as Bayesian Network and shap. In the backend, we have a prediction function. We would like to see what happened with it if we change the predictor a bit. Other methods are related to some accuracy metric, like Shapley Value Regression, random forest, and permutation. Our goal for this method is to monitor the impact of the changing of predictor value on accuracy of the model, R squared and root mean square error, for example. We can highlight the model agnostic methods of importance calculation. These ones are independent of the model behind the results. They are appropriate for all kinds of models. General idea how to calculate the importance here is based on simulation. The representatives of these methods are shap and permutation importance. The same two methods are also able to calculate the importance scores locally for each observation separately. It's quite nice possibility to have the importance assessed on the record level. Let's move to the part dedicated to the specification how these methods calculate the importance. I've chosen several methods of importance calculation to compare. Generally, the feature importance is a contribution of the single predictor in terms of prediction value or accuracy. There are different ways how to calculate the importance score. First method, shap, actually Shapley additive explanations, is an approach to explain the output of any machine learning model. It is a combination of combinatorics and cooperative game theory. In a nutshell, shap calculates the importance score as a difference between the original prediction and prediction for considered predictor set to 0, averaged for all possible combinations. Shap is a model agnostic method. For this presentation, shap algorithm has been used with simple linear regression. For Shapley value regression, the formula is equivalent as this one for shap. If you really want, you can perform these simple algebraic operations to convince yourself that these two lines are equivalent. The difference between shap and Shapley value regression is that shap refers to the value of prediction function, while the Shapley value regression is based on accuracy measure, R squared here. Importance is calculated as a difference between the accuracy of model with given predictor and without it. And then average is taken for all combinations. Shapley value regression and shap, based on linear regression here, assume the simple dependency structure between predictors and outcome. So if we want to look at the graphical representation of the model, it looks like this one on the right side. Bayesian network importance is calculated as a derivative of the response curve. It is a ratio between increment of outcome for given change of predictor value. There is also part related to normalization, but it only ensures that all predictors are treated the same way. Bayesian network is dedicated to modeling of complex data structure. You can say that it models interdependencies. We can assume that we face the simple linear model between predictors and outcome. Of course, it is reasonable only for independent variables, because if they are correlated, their structure is more sophisticated by definition. So it is justified to prepare appropriate network structure before the analysis for Bayesian network. For this purpose, there is an initial step with the searching the network structure using Tabu algorithm. The graphical representation of the model for Bayesian network can be more complex with additional connections between predictors. The next method is permutation importance. It is one of the most popular model agnostic methods to calculate the importance. The idea behind the algorithm is very simple and uses the fact that any association between the feature and the outcome is broken by the permutation of the predictors values. The importance is calculated as the difference between accuracy of the original model and model based on prediction with permuted values of relevant predictor. For random forest I used the impurity importance. The impurity importance of the predictor is calculated as the sum of all impurity for all occurrences this predictor in entire forest, not only one tree, but entire forest. The decrease of impurity is the difference between nodes impurity and the weighted sum of the impurity, measures of the two child nodes in the tree. The last method, standardized regression coefficients, can be helpful for comparison of the predictors ranking. Despite the poor usability, this method in terms of exact importance scores, it will be useful only to compare the ranking. Let's look at the idea how we can compare the methods. The simulated data was used to compare the methods. If you want to understand how the simulation was prepared, I recommend to look at the appendix. Now, I don't want to spend much time on technical things. I can only mention that all predictors are at the same scale, sampled by using beta distribution, and dependent variable is a convex combination of predictors with an error term. The number of predictors and strength of the relationship between variables were taken into account. I have tested 6 scenarios, 5 or 10 predictors included in the model, and 3 versions of correlation magnitude, low, medium, and high. For each scenario, I repeated 100 times sampling of 1,000 observations. Observations were sampled in that way to ensure the similarity, the simulated data, and the data with which we daily work in terms of shape of distributions, not only normal distributions, but also skew ones. The results of comparison will be presented in this template for each cell of the 6 scenarios. On this slide, I would like to show how to calculate the metrics used to compare the tested methods. Let's assume that we have 2 methods. Please be aware that the graph is based on fictitious data. Importance scores are normalized to sum up to 1. Our goal is to compare the results of these 2 methods. From the objective perspective, the methods may be similar in terms of different fields. If our goal is to deliver the ranking of predictors, we should focus on the match of ranking, whether the hierarchy of variables is identical. Spearman correlation is a good idea to use it for this purpose. It helps to answer whether the methods are consistent in terms of features order. Despite the same hierarchy, the magnitude of importance scores may be different. So if our goal is exact value of the score, we should use different diagnostic metric. One of the options is to use similarity based on Euclidean distance between the importance scores. Similarity metric is closer to 1 for more similar methods. There is no lower bound. Third way, how we may look at the quality of importance score is the ability to distinguish the result. Separability measures the difference between the best and the worst predictor, between the most and the least important. Please notice that the first 2 measures give us the one value, only one value. The third one is a measure for each method separately. Now I would like to show the results for each suggested metric for the simulated data. At the beginning, I will introduce the visualization, how to read it, because the visualization is for all 6 scenarios. The introduction will be smooth for only one scenario. The results for one scenario will be only examples, so please don't focus on the specific values there. It is useful only to understand how to read the next slide. First diagnostic metric I have used in comparison is a rank correlation. Here you can see a visualization of the upper part of correlation matrix for tested approaches. Shap, random forest, permutation importance, Bayesian network, and Shapley value regression. That's just an example, not the actual results. Here, the beta coefficients is also added. For the analysis of ranking consistency, it is justified to use the standardized beta coefficients. The color reflects the absolute level of correlation, raw value, but the size is responsible for relative value across all circles presented on this single graph. The smallest circle, the lowest value in the correlation matrix. We observe the highest correlation for Shapley value regression, shap, and permutation importance, and the lowest between Bayesian network and standardized beta coefficients. This plot shows the visualization of rank correlation between tested methods for all 6 tested scenarios. For low and medium relationships between predictors, we can see that all methods except Bayesian network are quite strong correlated. The ranking of the predictors returned by these approaches is similar. For high correlation, ranking is not relevant. For strong connected variables, it is hard to indicate predictor, which is better. In other words, the difference between the contribution of predictors for this scenario for highly correlated predictors is not significant. We expect the flat importance scores here. The second metric used to compare the methods is similarity. Just to clarification, that's just another example, not the actual results. As you remember, the similarity is an approach helpful when we are interested in the comparison of the results for the exact values of importance scores, not only hierarchy. The heat map shows the similarity between tested methods. Darker color means that the pair of methods are more similar. Brighter cells are related to the larger difference between importance scores. On diagonal, we have perfect similarity, and we can treat this color as an ideal benchmark. We can conclude from this chart that random forest and shap are alike. Similarity between shap and Shapley value regression is at the similar level as between Shapley value regression and Bayesian network. Additionally, we can use the hierarchical clustering to create groups of similar methods. Dendrogram on the top and on the left shows how we can cluster these approaches. The correlation matrix is the symmetric, not correlation, but symmetric matrix. So looking at the columns is sufficient. Shap and random forest are the most similar. The next one is Shapley value regression. Let's look at this visualization for all scenarios based on the number of predictors and collinearity level. For low collinearity, we can distinguish permutation and Shapley value regression as the methods with similar results. Permutation importance and Shapley value regression return almost the same scores. It follows that for the independent features, the increases R² for a given variable are not related to the combination of the variables included in the model. It confirms also that for this case, the permutation, the values for the predictor, and exclusion of variable lead to identical conclusion. For the other methods, we don't see common pattern. For medium collinearity, the group of 3 methods, random forest, shap, and Shapley value regression is visible. For highly correlated predictors, only Bayesian network and Shapley value regression create distinct common cluster, what is supported by the intensity of the color. Shapley value regression equates the contributions of features for this scenario, and Bayesian network create network which reflects the strong dependencies. Each variable has close connection with others. The last diagnostic measure is separability. This box plot, based on fictitious data, shows the separability, the difference between the most and least important score for one scenario, for one method. Each dot is a difference between the highest and the lowest predictor importance scores for one sample. Single point corresponds to one replication from the simulation. The results for this single point are based on 1,000 observations. The number of points presented on this box plot is 100 because we had 100 replications. The spread of results is an implication of the different distribution of marginal variables. Results for all scenarios are presented here. We expect that the higher collinearity, the smaller range of the importance scores. It is connected with our belief that for highly correlated predictors, the difference between the importance scores should not be significant. It is difficult to distinguish them in such a situation. Only two methods meet our expectations. Shapley Value Regression and Bayesian Network behave intuitively. Bayesian Network reaches a low level of range faster, already for the medium correlation. This is because that even for a moderate correlation between predictors, the structure of network has many connections. Classic permutation method doesn't take into account common relationships between variables, so we shouldn't be surprised that the level of the importance scope is the same regardless of the correlation. What is astonishing that the separability for random forest and shap is not affected by the correlation level. Let's move to the conclusion part. What are the implications? Diversity of methods we can apply to calculate the importance scores is really overwhelming. It is not easy to choose the best method. What's more, that is clear conclusion from this presentation that the choice of the best method is not possible, and it is dependent on many factors. Because the choice is strictly related to the data we analyze, we should be careful before choose the one method. The more important aspect than the number of variables is their collinearity. It should be emphasized here that only two methods, Bayesian Network and Shapley Value Regression, meet the expectation in terms of intuitive behavior for high correlation level. Another aspect we should include before making a decision which method is appropriate for us is the answer what we care about. If we are only interested in hierarchy, so for low or medium correlation, it doesn't matter which method we choose. The ranking is very similar for most of the methods. But if we want to obtain the exact importance scores, the decision needs to be thought out. On the one hand, Shapley Value Regression and Bayesian Network are in line with our intuition regarding the correlation level. On the other hand, main advantage of shap is the importance score at the respondent level. To calculate the importance for black box models, we have to use explainers, so shap and permutation is good choice. Finally, Bayesian Network allows to model complex structure in data, and it is easier to be in line with the theory using this approach. So as you can see, the choice is really not so easy. Here you can find a list of links with the extended description of the methods I used and mentioned in the presentation. Thank you for your attention.